Hello again. I think we can start, right? Yeah. Maybe I can close the door. So we're talking a lot about the orientation of the axis, where to put it. And we see that for synchronous machine. And we have a fixed rotor, or maybe rotating a synchronism with the field steady state condition. So that's what we did, the rotor. And because here we define two new axes, the axis and the q axis. And we need to do it because we don't have the uniform air gap for the whole rotor. So therefore, we did it on the d-axis and the q-axis dq coordinate system. But now, what we see that for induction machine, we have the uniform air gap here, and therefore we can have the different orientation that we can have, fixed to stator or fixed to rotor. And also we understand what is fixed to stator means. We are fixing the rotor winding here. Fixed to stator, that is the one, that's what we did. And if we look at the fixed rotor, that's what we have fixed winding for the rotor, then we are fixing the same axis as the rotor. So this is fixed rotor. And then we are talking about the fixed space vector. Now we are defining another space vector in somewhere, maybe here. This is space vector. And this space vector rotate with the space vector is rotating with a speed of one of the flux. So it's rotating this one. Now it's no longer fixed and it's rotating. So we can convert both the stator and the rotor quantities into this new orientation, new space vector orientation. That's what we can do. And for now, we define this one is the k, alpha k, and then we have also beta k. That's what we see. So if we have this new orientation, then we got the model of the machine like this. This is the equation that what we have developed. And then we also said that we would like to develop the equations such a way that we have, for now you can see we have four variables. One is the stator current and the rotor flux, and also you have the stator flux and the rotor current. We have the four variables here. But we want to develop the machine model such a way that only the stator flux, only the stator current and the rotor flux will be the state variable. This means these two here, stator current and the rotor flux will be the state variables. So if we want to have these two as a state variable, what we need to do, we need to replace in this equation such a way that we only have the stator current and the rotor flux as a state variable. So what we can do, we can apply first one thing in this equation, that we can write a rotor current something like as a function of the rotor flux and the stator current. So now we can replace the stator current, rotor current with this equation in the second equation. And then also we want to replace the stator current. We also want to replace the stator flux. And how you can do that? Then we put this R here. So now you can put this stator flux here and the rotor current to this equation. So we are replacing, we don't want this stator current, rotor current here in this equation, therefore we are replacing it to this such that it gives only rotor flux and the stator current as a state variable, as a variable. And then here we are also replacing the stator flux with this equation and replacing all this there. And if you replace this, then what will you get? And also one thing, if you remember that before we have this stator reactance, if you remember, stator reactance, we can write it mutual reactance plus a small part of the mutual reactance. That's what we see before. It's the one of the definition that we defined before. Then we can write it sigma S plus xm. And similarly, we also see that xr, we can write it 1 plus sigma r plus xm, multiply with xm. So this means we have the xx there. This xs, we can replace it with this equation. And we have the xr, we can also replace with this equation, with mutual reactance. And then you will find a final equation which is like this here. And we said that this is an asynchronous machine. This asynchronous machine means it could be a double FET induction generator or it could be a squirrel case induction generator. If it's a squirrel case induction generator, then we put the rotor voltage to 0. So we got this equation. When we replace this variable, now we have only the stator current as a state variable, and we have rotor flux as a state variable. Now that's what we have. And here I was discussing about the new variable. That's what we are defining before. In the new variable, what we are doing, we are saying that we represent the stator flux, rotor flux, psi r, which we can say 1 plus sigma r psi r. We have something in before. One, you can see that we have this. So we have capital R, we have a small r, and in between we have this term. This is the term we defined that, and we are using it to make a bit nicer model. So therefore we define this to have a bit nicer model. And here, 1 plus sigma r, this term is actually nothing but is xm over xr. And how it comes? It comes actually, we define two things. The first one, we define this like this, and the second like this. So we define these two, and then we inserted this IR. Yeah, this value of, we know that psi r, which is 1 plus sigma r, psi a small r, and in this small r, what we have 1 plus sigma r. This small r, if you remember, and here it is Sm is plus Sr Ir. And then again, we replace this Xr is equals to 1 plus sigma r Xm. Right? And then you can also replace this Ir with this equation. And you will have here two terms. Something with Is and then something with Ir here. And we select, let's say this is A, and this is B, and we select, say, A is equals to B. If you select A is equals to B there, and that will give you this term here. That will give you 1 over sigma S is equals to Sm over R. So if you apply something that I discussed here, and that will give you Xm over Xr is equals to 1 over 1 plus sigma R. That's what you will get. So if you have that, then you represent everything with the capital letter of the rotor quantity. Now you can represent the rotor flux with the capital R, rotor resistance with the capital R, and also you can define the new stator resistance, which is Rs prime. And in principle, it is original stator resistor plus you have the resistor with capital, rotor resistor with capital R. And this is what you will get here. And also you got another S sigma, and this S sigma is equals to actually stator reactance minus mutual reactance, and here this capital M. I put it capital M here. And what is this capital Xm? This capital Xm, which is Sm square over Sr. So this is something new variable that we need to define to make it a bit nicer model. Instead of a small r, now we are presenting as capital R. Instead of a small r here, we are also presenting all of them capital R, and we got the new mutual inductance. Now we are putting capital M. But they are a kind of the same. Like if you look at the losses in the system, in the rotor, and which is rotor losses, which is IR square over RR. It's the losses in the rotor, right? And in the new coordinate, in the new variable that we define is capital R square, which is capital R square, these two part. And if you insert this capital here this capital IR, which you have only this 1 over sigma R with the small one, this means you put it this one, you are getting this one a square, and the capital R square you are getting, no, it should not be a square here. So what you're getting 1 plus sigma square, then you're getting this one part is cancelled with this one, and you're getting same as this one. So this means this part, they are same actually. So you are getting there, this one is the same as this one. They are same, but we now got a new variable such that they will simplify our modeling. So we have now the simplified modeling, and this equation, they are for asynchronous machine. Now if we want to make them for squirrel cage induction machine, and we see that in the squirrel cage induction machine, both in are shorted. This means the voltage, rotor voltage is 0. So you can put this part, rotor voltage part to 0. So you can put the rotor voltage part, this part to 0, and this part to 0. And if you put these two parts 0, then you are getting the induction machine equation. So now we got the new induction machine equation. And also you can see that all the new variable here are capital R that we defined in the previous equation. And the voltage is here 0. And another term related to this, that's also gone now. So I'm not discussing how you come to this in detail model, but this is the model now we obtain. And we have the two state variable. One is the stator current and the rotor flux. And then we have the nicer equation for the torque. This is a torque equation. Now we have everything that's what we need. So if you also want to look at in the block diagram form and how this model look like, and if you see that this induction machine, you can write it something like this. You are giving US as input. Yeah, so if you derive the transfer function, then you will see that this term you can write as SISK in the Laplace form. There's the SISK you can write in the Laplace form. Then you'll see that you are getting something like RS plus RR plus S sigma omega n minus something j omega. And then you have one term for this part. Let's say this one we define as a E. And then you have something E here. And then input is US. And the output you're getting is IS. So the equation that you have here, this US, and if you convert them into Laplace domain, this is SISK, you can write. And then you can write it in a block diagram. Then you can see this is your machine, and you are getting the output IS, and you have the input US, and this is the feed-forward term. This is your machine equation. So now you have this induction machine. This is the machine. And then later, if you want to implement the control, like the current controller, PI controller, and then you have the current reference here, ISREF, and then you are getting this feedback. Then you can implement the control, right? So that's how we have the machine, and we have some cross-coupling term, some decoupling term. Like you can see one feed-forward term here. And this is, we have also one decoupling term, then you can remove this. That's how we can develop the machine, develop the control. But for now, we are not discussing the control yet. We'll discuss the control a bit later. But first thing, what I want to say that now we got the machine model, the equation that we need to understand more detail. So this is the equation that we will use. These two equations mainly here. One is the stator voltage, one is the rotor voltage, and the torque. This is the equation that we have. That's what we need to develop the control. So you got the machine model. And then we are discussing the orientation, and also we see that if it's in a stator orientation, then still there as a quantity, and then Fk is 0. And if it is rotor orientation, then Fk become n. In the rotor equation orientation, Fk become n. And then space vector orientation. The last one is the space vector orientation. And we will say that we will orient it with the rotor flux. So we will choose one of the space vector, which is the rotor flux. And this is the rotor flux. And we orient in this coordinate here, in the rotor flux orientation. So what do you see in the rotor flux orientation? If you see that, we have all the rotor flux in this here. This is in the alpha axis. So you will see that psi r alpha, which is psi r. And what do you see psi r beta? Beta component. What is the beta component here? It should be 0, right? Because we oriented here all this in the alpha axis. So we have nothing here for the beta coordinate. So you got it 0. And if you want to look at the equation, how they look like when it's a stator orientation model, then you will see that US, which you are getting, RS, stator orientation, plus IS, plus D psi S, DTE, and then for the rotor part, you are getting URS plus RRS, IRS plus D psi S over, no, this is R S, and you got minus J psi r is for stator orientation. And then if it's rotor orientation, then you are getting, for the rotor orientation, you are getting USR, which is RSR ISR plus d psi SR dt, and you have something here plus J N psi S R. And if you look at the rotor, and they remain the same as, which is UR R is R IRR plus d psi R dt, like this is the rotor orientation. So when you are getting the stator orientation, rotor orientation, now you have this part because of this orientation. Rotor orientation, you are getting this part with the stator, but for the stator orientation, you are getting this part with the rotor equation. So now we know that different orientation, and the last one is space vector orientation, that we defined alpha k, and for this alpha k, and we got the fk frequency, that's what we developed. So we want to discuss a bit, maybe we don't need to discuss this part, this stator oriented model that we have already developed the equation in the previous slide, but this is the, when we present the stator current and the rotor flux as a state variable, then we got this equation, and that comes from the equation that I presented here. So this is the equation, and then when you present in the stator orientation and then do the same, all this work, then it gives us finally this equation in the stator orientation. But we are saying that we represent them into a rotor flux oriented model. If it's rotor flux oriented model, then what we see that the alpha k, this is the alpha k, that the new coordinate system, and is now in the direction of, so we have now this in the direction of the rotor flux. If it's direction of the rotor flux, then what we see, we have only the alpha component of the rotor flux, and the beta component of the rotor flux is 0. Since now we present this in the alpha axis, the rotor flux, so we have the beta component of the rotor flux is 0. Since the beta component is 0, the derivative part of the beta component is 0. And then if you also look at the angle, before you have the theta k, and now you have this theta k, which is the angle of the rotor flux. And then we have the theta r, which is this one that we define here. And then finally, we can write the angle equation, the rotor flux equation, the rotor flux angle equation here. This equals to the theta. Theta is the angle between the stator and the rotor orientation. And then this is the angle between the rotor and the rotor flux. And that's how we can define. So now we got this term. And now we want to see how this equation look like that we develop in the, before we are saying that it's in the K. Now we have them in the rotor flux orientation. Then now we want to see how it look like. Yeah, this term here for induction machine, it is 0. So we got this. And here, this part, we see that this voltage should have two components. One is the US alpha plus J of US beta. We have two components, right? So first equation, you have two components. One is the US alpha. One is the real part of this equation, and one is the imaginary part of the equation. Similarly, rotor equation, we also have two parts. One is the real part, one is the imaginary part. So if we separate the real part and the imaginary part of that equation, now we are looking at imaginary part and real part of this equation. And if you look at the real part and imaginary part of this equation, what you will see, you will have on the real part, the alpha part, and also you'll have the beta part here. Alpha part and the beta part of that equation. And there are some other terms actually, like for example, you have minus f of r and psi r beta, and also you have like plus 1 over n tr psi r beta plus 1 over n psi r beta dt. But we do not put this since the beta component is 0. Beta component is 0. Therefore, it's not necessary to put these two components. Therefore, we don't. Yeah, it's not necessary to these two, right? Because the beta component of the rotor flux is 0. So therefore, we have only these two equations. And from that, what we see from this equation, we can write from this part. You can write the first differential equation of the rotor flux. So from the first part, we can get this equation, and from the second one, the second equation, beta axis, we got the frequency of the rotor current. So from this one, we got the frequency of the rotor current here, and this gives us these two. Any question here? We will also check the alpha beta component of first equation, but for now, we check only the alpha beta component for the rotor voltage equation, and we see that from the rotor voltage equation, we can calculate the rotor current frequency, which comes as a function of the beta axis current and the rotor flux. And also we got the derivative equation, first order differential equation. That's what we will need for later when we develop the model, when we derive the steady state characteristics. So now we got these two equations here. These are the two important equations now we got here. We will discuss them further. And also if we look at the frequency, and we see that this is the angle here. We have this is the angle of the rotor flux. And if we derivate this, if we apply the differentiation, that gives us the frequency Fk, which is the frequency of the rotor flux space vector. This is the frequency that it's rotating. And the main purpose is to check the frequency of that and how we can present it. And you can see that previously we got Fr, which is equals to this from the beta component of the equation. And also you can write Fr is equals to Fk minus n. And from this you can write the frequency of the stator flux, which is the rotor frequency. This is the speed that rotor is rotating, plus this small deviation. This is the deviation between the main space vector and the rotor frequency. So we see that's how we can get the speed frequency of the space vector. So what we see from the rotor equation, we see that we can get this differential equation for the modeling. That's what one relation that we see. And the another thing we see that we can get the frequency of the space vector from the rotor part. And it comes as a function of the stator beta axis stator current and the rotor flux. Now we want to see the alpha beta component of the stator voltage. So we have the stator voltage alpha beta component, the first equation, and then we got the alpha beta component of that equation. And it's after some rearrangement. This is the alpha component, and then you have the beta component. And we did some rearrangement, like the voltage, it was here, then we put it right side, because this would be the 2-hour control voltage. So we got this equation, this alpha beta component. Since we want to present them into differential form, so therefore we put this differential part in the beginning of the equation, and then rest of them in the right-hand side of the equation. So that's what we see here. And one interesting thing from this, what you see, we have the two components of the current. One is the alpha component, and one is the beta component. Now we see we have the two components of the current. And what you see in the rotor flux, this is the rotor flux equation, and you see then rotor flux depends on the alpha component of the current. So this means if you control the alpha component of the current, then you can control the rotor flux. That's the one thing, that's what we notice here. And the second thing, if you look at the torque equation, this is the torque equation, and after some rearrangement, you will find the torque equation like this, and you can see that in the torque, we have this term, the beta component. So this beta component is controlling the torque. So what you can see that if you control the alpha component, this means you can control the flux, rotor flux. And then if you control the beta component of the current, then you can control the torque. And this is the main two principle that we apply. We control the torque of the machine, and we control the flux. For example, in the field weakening, we need to reduce the flux, then we need to control the flux. And if you control the beta component of the current, then you can control the torque. Yeah, if you look at the torque, here you can see that this part, the beta component of the flux is 0 because we oriented in the alpha coordinate. Therefore, we got this part to 0. This means this part is 0. So we see that it's only the beta component of the current that's contributing to the torque. So now we can have the current, alpha component, and also the beta component, and one of the component is controlling the rotor flux, and the other component is controlling the torque of the machine. And if you look at the DC machine, it's more like the same, right? In the DC machine, we have also one component is the armature. The armature current is controlling the torque, and the field current is controlling the flux linkage. So it's more like the same. One of them controlling the torque, and the other one is controlling the flux. And this is the same thing that we notice also in the synchronous machine or PM machine. So now we want to see that we have only from the converter that give us the controllable voltage. So we can provide this 2 voltage from the converter. If we provide this 2 voltage, that give us the current. Now we also put instead of K is psi R, is because now we are saying that is the rotor flux orientation. Therefore, we put it psi R. And what you see here, we have some component like in the first equation. Yeah, after rearrangement, you can see that we have some cross coupling term, like this part is this part here, we have this beta component of the current in this equation. So it's an alpha component of the current differential equation, but you also have another cross coupling term there. So you have one cross coupling term, and also have one cross coupling term. So this means when we develop the control, then we need to put some cross coupling term to canceling the effect of this cross-coupling component, and also you have some feed-forward term. You can also cancel the effect of this feed-forward term. So when we design the control. So we can omit these two components, cross-coupling term and also the feed-forward term. Then we can neglect this component when you design the control. The same principle that we did for other control. Then we can independently control these two currents to control the field and also the torque. And by controlling this current, then we can control the field. By controlling the beta component of the current, we can control the torque of the machine. Any question here after this? Any question? So what we are talking about, our main intention is to control the torque and also control the flux. So now we can control the torque by controlling the beta axis component and control the flux by controlling alpha axis component. But which flux to control? There are many flux, right? One is the stator flux, rotor flux, and the air gap flux. Which flux to control? That's also an important point that we mainly, when we control the field-oriented control, rotor field, then we control this rotor flux. And then when we implement the other control, like EU over F, voltage frequency constant, then we use this one. We don't control that much. We don't use the control based on this air gap flux. So the first two, the first and the last one, we mainly control. Here we're talking about the rotor flux controller mainly. If you remember, in the rotor equation, when you are developing the equation, then we are presenting some of the new definition, new variables, like the small r. We present them into capital R for some sorts of representation, so you can present the model a bit nicer way. So we also did the same thing here. We present, like you have this IMS, is the magnetizing current, stator current, IMS. And we can see that a stator magnetizing current like this, how we get it is from, like we have this XM, the psi S, which is XM. No, not XM, it is XS, IS. I omit the K for now. And then XM, IR. And then you can write it, this XS, we say that this XS you can write is 1 plus sigma S XM IS plus XM IR. And then you can take the XM out, then you are getting 1 plus sigma S IS plus IR and then XM. And then this part here in the middle, the current, we define this current as a magnetizing current of the stator. That's how we got all these three equations here. One for the magnetizing current for the stator, one for the magnetizing current for the rotor, and the one magnetizing current for the air gap. So this is some definition that we need to use later. That's how we got this variable. Yeah, this is how we got this variable. And then we have the complete transform model. This is the model that we already developed. It's a mistake here. It should be M. So we have this model. Now we want to look at the steady state characteristics. So this is the model that we are discussing a lot, that we have the model. And once we want to find the steady state characteristics, what we do, we put the derivative part to 0. If you put this derivative part to 0, then you will get this model here. You have the steady state characteristics in synchronous rotating coordinate. Now we are saying that they are now in synchronous rotating coordinate because we are assuming that alpha k is now rotating with a space vector, CR, rotor flux oriented control. So it's now rotating, and therefore we got these two equations in the steady state when we put the derivative part to 0. So now we got this model, and we put the derivative part to 0. And then what we do, we can do some rearrangement here. Like in this equation, we can insert here the psi s and psi r here. This is the first thing that we do. We inserted the psi s and the psi r in these two equations. And secondly, we also did in the second equation multiply with fs over fr. First, we inserted the psi s and psi r in this equation, and then in the second equation, we multiplied also fs over fr. And why we are doing this, we want to see the characteristics, steady state characteristics, so we need to do some simplification that give us a nicer model. So in next, what do you see? If you inserted the psi s, psi r, and also multiply with this fs over fr, then you got this model. And in this model, one nice thing that what we want is that these two terms are equal. That's why we inserted this psi s, psi r, and also multiply with fs, fr in this equation, so that we can get this term the same in the both equation. And now it's in the rotating frame. This means all are DC quantity. So if we want to draw a circuit diagram of these two equations in the steady state, and you can see that, and we have the input, the stator voltage, which is the stator voltage input. We have the stator voltage input, and the drop across the resistor